All right, hopefully that worked. So hello everyone. Hello and welcome again. Today we're going to build data pipelines with Spark, with big qualifying quotes here. I'll talk more about that in a second, but thank you for coming. This is going to be an interesting session, so be prepared. I should also probably have the correct window in focus. There we go. So, in case you haven't seen me before, this is more for the online stuff. I'm Beege. This is the stuff I've done. This is the places I've worked at. Basically, this is why, this is my argument for I swear I know what I'm doing, except this time, I really don't know what I'm doing, but it's going to be a great time. So, moving on. So, to be absolutely clear, I'm more of a database guy, not so much a Spark guy, not so much a data frame guy. I do not understand these things. I don't understand why they exist, kind of. I do a little bit, but we'll talk about that. So, the knowledge I'm going to give you is very incomplete. I want to be upfront about that. This is meant to be introductory, okay? Especially because when I first started to prepare this, I had a completely different understanding of what this whole thing was. So, I'm hoping I can save you guys about 12 hours, because that's how long it took me to figure this stuff out. And everyone can have a great time. But this is, to be perfectly honest, this is going to be a shit show, but we'll try to make it fun, all right? So the agenda's pretty short, but there's going to be a lot of content. It's just there's not a lot of bullet points, okay? So we're going to start with, where did Spark come from? Okay, why does Spark exist, right? Then we're going to talk about what exactly Spark is. We're going to talk about the datasets and data frames model, which is not the only way to use it, but because we've done a lot of SQL stuff before, Spark does have a SQL interface. We're not going to cover the SQL stuff today because, it's SQL, man. You can pick it up in 2 or 3 days, which I'll rant more about that later. And then we're going to try running Spark on Kubernetes. We're also going to try running our own pipeline. It's going to be a little bit of a demo. It does work. It does work. It just doesn't do very much. But, yeah. Any questions before we get started? Spectacular. Here we go. All right. So, I had a little bit of fun with this. Where did Spark come from? In the beginning was the file. Developers stored data in the file, and it was good. Then there was the database. The database structured the data. Developers set up databases, and then they queried the data from the database, and it was good. Then there was Hadoop. Developers returned to files, but they retrieved data from many files at one time. They wrote MapReduce algorithms to retrieve the data, and it was good. If you don't know what MapReduce is, we'll get there in a minute. And then there was Spark. It also used many files, but it used them in memory. Developers ran MapReduce algorithms against memory instead of reading from disk. Their data was retrieved faster, and it was good. So that is where we are today, Spark. Now, does anyone not know what MapReduce is? Okay, so MapReduce is, the name makes sense from a computer science perspective, but if you don't have a very strong theoretical background, it's what the hell does that mean? So MapReduce is you map some sort of operation to many different workers working with many different data sources, e.g. many different files, okay? And then they all fetch the relevant data from all their files. They send it to some place to kind of aggregate centrally, and then they reduce it. They basically deduplicate, do grouping, all this kind of stuff, okay? So really, MapReduce is just a way to do distributed computing, okay? You map your function out to all your workers, you fetch your data, and then you reduce it into a format that you can actually work with and use. I'm simplifying. That's a little bit wrong. I have not read the MapReduce white paper, but that has been a good enough understanding for me, and I'm hoping it's a good enough understanding for you too. But if you want more detail, there is a white paper on it. It was a very, very big deal when it was published. I do recommend reading it if you find that kind of stuff interesting, but I am very lazy, so we'll move on. So what exactly is Spark? According to their website, they say it's a multi-language engine for executing data engineering, data science, and machine learning on single-node machines or clusters. The hell does that mean? So basically, it's distributed in-memory data processing engine. Okay? Distributed meaning it can run on multiple computers at one time. Okay? In memory, meaning it happens in RAM, so it's fast. Okay? Remember, RAM is fast, disk is slow. And it does data processing. It has a whole bunch of libraries and APIs and various little functions to do data processing, much like a database, if you're familiar with a database. If you're not, we're going to have a great time. It also solves the problem of huge data. Okay? Spark and Hadoop came out of the big data era, which was right before the kind of AI era that we're in now. Okay? So around when Facebook was getting big, there was the idea of recommendation algorithms, right? Today we kind of call recommendation algorithms machine learning. They're more just very simple statistical, well, very simple, quotes, big air quotes there. Simpler than machine learning, statistical models. And the way you would build recommendation algorithms and these kinds of things, you needed a lot of data to do it. So that's where kind of the big data era came into play. And that's why MapReduce was created. Because once your database gets up to hundreds and hundreds of gigs, querying it is not so easy on one computer. Because with traditional databases, right, it's vertical scaling. If your compute can't handle the workload that you need, you get a bigger computer. Okay? It's around that same time that you also saw NoSQL systems come out, like MongoDB and these kinds of things. So Hadoop and Spark solve the analytics side of big data. And then NoSQL databases like MongoDB, CouchDB, CockroachDB, all those, they handle kind of the transactional side, like the website side of big data. Okay? Does that make sense so far? Cool. Also, Spark provides the dataset or data frame data model for ease of use. Who here knows SQL? 1, 2, 3, 4. Okay, most people. If you're like me and you're very comfortable with SQL, you're going to hate this. You're going to be like, why? Why? At least that's my reaction. It is a way to do SQL-like set logic and operations using a standard kind of programming model, right? Because SQL, it's set logic and it's more declarative, right? Whereas when we do normal programming, it's imperative. You just say the steps you're going to do, right? And then the program executes in order, right? You give it a set of imperatives, a set of commands, and it follows the commands in order. In SQL, there isn't really an order. I mean, there's an order of your syntax, but there's not an order to the logic, okay? Internally, in the database engine, right, it does a whole bunch of logic of, okay, I should filter here, then I should join, then I should filter, then I should filter again, then I should join. It does all that for you. You just declare the logic you want, and it figures out the order. Imperative programming, what we normally do, is more step-by-step. Does that make sense? Cool. So it takes the kind of set logic, the declarative nature of SQL, and makes it more of an imperative kind of procedural nature for people who don't know SQL, even though it only takes a couple days to learn. Damn it. And a big thing is that Spark runs in the JVM. And you might be thinking, but wait, Beege, I keep hearing people use Python with Spark. We'll get there in a second. Spark itself runs in the Java virtual machine, okay? So if you want to do like native stuff, you would want to write in either Java or Scala. It provides APIs for both. Of course, since it's a JVM, since Kotlin is Java compatible, theoretically you could use Kotlin too, but I haven't found much documentation on that. It's pretty much Java, Scala for native development. But we'll cover Python stuff in a second, okay? And one thing I want to be very, very, very clear about, which was a big misunderstanding I had. If you're familiar with Hadoop, Spark is pretty much Hadoop, but in memory with some nice APIs, okay? It is not a data pipelining system, which I took way too long to figure out, okay? It doesn't have a whole bunch of the nice things you would expect from kind of a data pipelining platform. It doesn't have orchestration. It doesn't have scheduling. It doesn't have task management. None of this kind of stuff. It is not a data pipelining system. It is only a distributed computing and data processing system. Full stop. Okay? At least that I've been able to figure out. I could be wrong, and maybe there's parts that haven't happened, or that I haven't gotten to yet. But yeah. Now, that said, if you do search for Spark and data pipelines, you will come up with ML data pipelines in Spark, which you can use it to do the distributed computing of machine learning. But that's not like a data engineering pipeline. That's a different kind of thing, okay? So it is not a data engineering pipeline system. That said, you can use it with a data engineering pipeline system. You could have some other tool like Airflow or Prefect or whatever. We've done presentations on Prefect before. Actually go pull data from an external source, dump it into like a Hadoop file system, an HDFS, and then have Spark do stuff on that, then pull the results out and do whatever. Spark can fit into a data pipeline system. It is not a data pipeline system itself. Okay? Is that clear? Has everyone got that? Cool. It took me way too long to figure that out. All right. Any questions before we move forward? So.
Yeah, thanks for explaining the differences. I just have like one more question. Since it's an in-memory data processing engine, is there any like limit to how much it can run? Like, for example, if you have limited RAM, is it limited by that amount of RAM?
Yes. So that is what, but that's why you do distribution, right? So you scale out your workers, you try to parallelize as much as you can. Actually, when I was preparing this, I was hitting out of memory errors because I was using about a ½ gig data set, and the JVM is not very memory efficient. Well, that's not true. The way I was using it was not very memory efficient. So you do have to be aware of that. If you get into like really like fine performance tuning stuff, you may need to mess with your JVM settings, maybe increase the heap allocation for the JVM so that it can use more RAM, all that kind of stuff. But we're not going to go that deep today.
Is it possible to kind of like use the mmap, like mmap or mmap for the...
I don't know what mmap is. Do you want to tell me?
Like usually when we don't have enough of RAM in the PC, we can map it to, I don't know also exactly how it works, but we can map into some memory with like,
Map disk to memory? Yeah.
Here it says the Unix system calls that maps files or devices into memory.
I think that's if you're doing kind of like embedded systems programming. Like let's say you have like an LED screen or something, and you want to just write data directly to that LED screen, you can probably just map it to some memory address and then write to that memory address and it'll output on the screen.
But not for this for files, for example. If our file is too big to go through the RAM, we can map it to the memory in the file system somehow.
So that's just swap, right?
Yeah.
That's what swap does. Now, I haven't gotten into the performance stuff. Honestly, I barely even got into the parallelization and distributed computing stuff because I spend so much time trying to figure this thing out. But there's kind of two ways you can handle it. You can either increase the heap allocation in your JVM, or sorry, 3 ways. Increase the heap allocation in your JVM, or more in line with Spark, get more hosts, or you could just optimize your code to be more memory efficient. There are, like, it does a whole bunch of optimizations internally so that, like, if you're reading data from disk, I haven't gone into the internals. I am guessing this is probably wrong, but if I was building something like Spark, I would imagine what it does is it looks at if you're reading from a file, for example, and it kind of indexes it, and then it pulls it into memory as is necessary. That's how I would guess it works. But again, I'm not sure. I did not build Spark. I haven't had a chance to go super deep into it. But it seems to be relatively efficient. Now, one thing I want to cover with this. Yeah, what's up?
Like, how would you define huge data? Like, at what point should I try to introduce this into our company's stack?
I had the same question because when I was using it locally, I was like, it takes like 5 seconds to spin up. What the hell, right? So I started looking around, like, when do you use Spark? You should only use it for big data, or unless you're not in too much of a hurry and you're comfortable with the Spark API. But the things online I was seeing was like 1 to 10 million records is when you want to start considering Spark. But honestly, I feel like that's a bit low. Like, That sounds suspect to me. Unless it's like very, very wide tables, in which case, okay, yeah, sure. Maybe tens of millions of records would merit Spark. But I think it depends on the type of operation you're doing. But I think in most cases, unless you're doing like heavy duty data analytics, you don't need it. In my opinion. I have not needed to use it until preparing for this. But I have worked in companies that used it. When I worked at PUBG, currently Krafton, formerly PUBG, they did use Spark for their data analytics because they had millions and millions of players generating billions of records of data, and that was a great use case for Spark, and they used it very effectively. But I did not use it directly myself. I was not part of that team. So there are use cases at larger companies or with huge amounts of customers, or maybe you have a lot of machine-generated data. For example, let's say you're doing like something with logs and the log volume ends up being absolutely huge. That might be a good candidate for Spark. But many applications don't generate enough data to really need it. Or if you're looking at very long historical data. Like,
can it handle like big files?
oh yeah.
Huh?
You want to do partitioning, but yes.
Yeah, okay.
Yeah, so Spark is very compatible with HDFS. So if you basically partition your files according to the HDFS format, you're good. Now, when it comes to like the big data versus like, should I use Spark, should I not use Spark? Maybe if you've gotten maybe if you have gotten comfortable with the dataset and data frame API, which we'll talk about in a minute, but you don't want to use Spark because it's like a sledgehammer, right? If your data's this big, you don't want to use something as big as Spark. The general recommendation online seems to be using Pandas, or more recently, Polars. Polars appears to be just a more optimized Pandas. Our data scientists at my company use Polars, and they love it. To the point where they're like, hey, can you just give us files instead of a database? And I'm like, I hate you. But yeah, Polars seems to be pretty nice. It has a good balance of when to read from file, when to read into memory, these kinds of things. Also, I should have my notes up. There we go. Oh, and last thing, I mentioned earlier, it runs in the JVM. If you're wondering, like, hey, but I've seen like using Spark with Python. There's a tool called Py4j, which basically allows the Python interpreter to access Java objects in the JVM. That's how it does it. So they just built a Python library around Py4j, and now you have Python with Spark. So that's how it works. Any questions before we dive into data frames and stuff? Cool. So data sets and data frames. Using the Spark API, they can pull from various sources. So if you have JSON data, Parquet data, Avro data, CSV data, if you want to pull SQL out of a database, Spark can do that. It has APIs written to support all of these. Sometimes you need to do a little bit of funky stuff, kind of reaching into the JVM directly, rather than just having pre-written Python functions if you're using PySpark. However, it seems to be well documented, and it does work quite nicely. Well, sometimes the documentation is a little light, but there are plenty of examples online. And it is important that it works with all these different formats. Is anyone not familiar with Parquet? Okay, so you know JSON, you know CSV, right? They're text-based formats. But let's say you open up a JSON file and you want to find a certain attribute in a certain object. Let's say it's an array, right? So let's say it's a JSON array of like 1 million objects, and you want the name attribute of the 1,000 or 165,002nd element. How are you going to do that? You have to parse the whole JSON file into some kind of objects, and then you have to iterate through, and then you have to find the attribute, right? Very expensive. Things like JSON and even CSVs are not indexed, right? You can't just jump to an arbitrary point in it. It's also not structured for quick parsing of attributes, right? It's meant for human readability. Parquet, however, is different. It is a binary format. It is also columnar, which means that it's great for analytics. Okay? So if you want to do aggregations, sum, average, standard deviation calculation, all these kinds of things, way faster in Parquet. Additionally, Parquet is indexed. If you want to find a particular record, you can do that. Granted, because it's columnar, what it has to do is it has to go through the index column or the identification column first and then go find the values for that row in the other column, so it's not as efficient for looking up rows because it's meant to be an analytics format. But it is a very popular analytics format. It's very fast. If you're working with modern data scientists using pandas and polars and these kinds of things, there's a high likelihood they want to use Parquet. So it's a good format to know about. Avro is kind of a similar thing. I forget if it's columnar or row-based. I'd have to look it up, but I haven't heard of anyone using it. Like, I hear people get excited about it, but no one using it. So, I don't know. Maybe I just have worked at the wrong companies. Now, if you look in the Spark documentation, there's technically like 3 or 4 ways to access the data. There's something called resilient distributed data sets in Spark. Okay? These are related to the Hadoop file system, okay? Which, if you're working with like CSVs and JSON and stuff, that's not Hadoop. At least, I mean, you can make it Hadoop, but you have to do all the partitioning and all that kind of crazy stuff. Now, your average person doesn't understand Hadoop file system very well. It's something you have to go study, all that kind of stuff. I have not studied it. And so they found that basically using the RDD API directly is not very popular. However, Pandas came out, and they're like, hey, this data frame thing is kind of cool. So they had this abstraction over RDDs. They call them data sets. Okay? So you might be thinking, Beege, what the hell is this like RDD, data set, data frame? What is the difference between all of these? So an RDD is the old style. Generally, you don't need to worry about it. Okay? A data set is something specific to Spark. It is a strongly typed collection of data. Okay? A data frame is loosely typed. And the idea is pulled from Pandas and is the default way of doing it with PySpark. So it's highly likely that if you're not highly likely, if you're doing things with PySpark, you're using data frames. That's it. GG. We're going to use PySpark today, so everything's going to be data frames. But if you hear some Spark person say data set, you know what it is. It's like a data frame, but it's strongly typed, usually in the Scala, Java land, not so much the Python land. Make sense? Cool. Now, that said, Spark provides multiple APIs for accessing and manipulating data. There's a SQL API, so you can just write SQL, but like I said, we're not covering that today. And then there's the dataset API, also data frame API, whatever. Now, do note that all these things under the hood are really RDDs, okay? But you don't need to see that as a user. As a user, you won't mess with RDDs directly. And then in terms of, okay, these are data sets, these are collections of data, what the hell does that mean? Basically, they're similar to tables. They have rows, they have columns. Woo! Why aren't we using SQL? Because a SQL database can't span hundreds of machines in a distributed manner. That's why. So data sets or data frames, they are organized into rows and columns. Like any other database system, they support filtering, they support aggregations, pulling out specific data items. That's all good. If you've used database before, there's not a whole lot of new stuff except the way you do things. They also support various aggregation methods. So, you have your like max, min, average, all this kind of stuff, calculating standard deviation, all these fancy things. Not anything terribly surprising there. So, but the nice part is that from your data frame, when you pull the data out, it's already in your language. You don't have to do any sort of crazy parsing stuff or like type conversion or any of that because it's in your environment already. So that's a big advantage it has over SQL. So if you need to pull it out and do some statistical calculations that you couldn't do in something like SQL, no problem. It's already in Python or already in Java or whatever it is you're using. So does this make sense? Any questions about this? Cool. All right, so now I should have made a slide for this. I did not make a slide for this, but we're gonna run Spark, and we're gonna do it on Kubernetes, and I'm gonna rant for a while. I'm gonna be really angry. If it gets to be too much, tell me to chill out. But here we go. Let me just clean up my workspace here. Excuse me. And here we go. No. There we go. Okay. Okay. Great. So. Oh, I hate you so much. All right. So couple things. I need to share a GitHub repository with you guys. I will send it in Discord, but I will also put it on the screen. I'll also put it on the screen here, okay? So if you go to GitHub and go to CodeSoul, I'm also going to share it in Discord if you're on Discord. If I could find the channel, there we go. You can clone this repository down, and then rapidly learn to hate yourself like I do. So I tried to make the README as clear as possible with as much code samples as possible. So don't worry about the Kubernetes stuff for now. We're going to do that in a minute, okay? Right now, the only things you got to worry about are setting up your Python environment, okay? So typical Python environment setup. I use just straight pip. I don't use poetry. I don't use Anaconda, like, ugh. And then don't worry about this. We'll get to this later. Oh, I forgot to include. It's fine. I'll just explain it and I'll update the thing later. But if you just, actually, you don't even need this line. If you just do these after you clone it down, you're good to go for now. And then we'll cover the crazy stuff after that, okay? So I'm going to give everyone a couple minutes to clone this down if you want to follow along. You don't have to follow along, especially if you only have 2 gigs of RAM, apparently, because your machine will be sad. The data set we're working with is 500 megs. So, yeah.
I just read it in the swamp.
So since that's in the README, I'm not going to just keep this on screen here. The data that we're going to use, and I'll also share this in, actually I think I shared it in the README already. Yeah, it's in the README already, so you can just check the link there. But we are going to use this data set that I found on the interwebs. This is on Kaggle. This is an analysis of higher education in India. So it's 500 megs of CSV files. Oh, baby. You want to start downloading it now. I'll also just put the link in Discord so you don't have to go rummaging through the README. Ooh, hey, Discord, you don't need to be up there. There we go.
You have it linked in the GitHub README as well? Or?
Yes. And then, if you want to take a preview of the files, it was a bunch of surveys conducted over the course of like 5 or 6 years or something like that. It's a lot. These extra folders are basically the same data but split out by year. I don't know why they did duplicates. The data set's actually a lot larger than it needs to be, but whatever. So because it's 500 megs, I recommend downloading it now because it's going to take a minute. Hey. You can worry about it afterwards. It's fine. Yeah. So go ahead and download this. And I think I've covered enough time. So, has everyone got the repository cloned down? Cool. Is everyone starting to download the data? No? Okay, I'll wait a minute for you guys to download the data. I don't want to wait for the download to finish, but I do want to at least make sure you have it started downloading. Especially because all of us are going to be pulling down 500 megs on the same Wi-Fi. Yeah. In hindsight, I should have chosen a smaller data set, but it's fine.
ETA is like a day.
Okay, that's not bad. All right, has everyone got the download going? All right. So, as usual, I'll just kind of describe how I set up the project. So, now I'm not necessarily saying this is the best way to do it. This is just how I like to do it because I don't like adding more tools. Poetry looks really cool, but I don't want to install another thing. So this is my PyProject.toml. I define the dependencies here. We install PySpark. We install NumPy. We, oddly enough, need setup tools. And I install Pandas as well, just because outputting the data to disk without Pandas is just a giant pain. Because Spark wants to do everything in HDFS, and I don't want to deal with HDFS. So Pandas it is. Do you need help? Power, you got to come up here. Yeah, sorry, dude. And that's pretty much it. Once you've got that done, once you set up your virtual environment and you do pip install dot, it'll work. That's all in the README. In terms of how this is organized, the key parts are in the source folder, the pipelines module. The main is the main. Surprise, surprise. With Spark, or with PySpark at least, you need to make sure you have a Spark session set up. Why? Because it runs in the JVM. Python does not have a JVM, right? So you need to get the Spark JVM up and running, and then initialize a session to connect to it. And then your PySpark library can send requests to the JVM to do the work. Okay? So that's why the Spark session stuff exists. This is kind of the standard way to do it. And then you will need the Spark session to initiate Spark operations. In my case, I just pulled my actual pipeline out to a separate file. And then I passed the Spark session to that. Also, make sure you stop the Spark session when done, so that stuff shuts down properly. Granted, it's just the JVM. It's not a big deal. Once you kill the process, the JVM dies anyway. But it's just nice to do a graceful shutdown. Any questions about this one so far? It's pretty basic. All right, moving forward. So this old pipeline here, this is the example that I found on the website for basically doing a prediction. For now, because you're probably still downloading the data, what I would do is I would just rename this one as new pipeline and rename this one as pipeline. Just kind of swap them out. And then you should be able to run Spark. Now, what am I doing? There we go. There we go, that's what I want. Wait, is that what I want? No, that's not what I want. I'm totally prepared, guys. Okay, so now, one of the reasons I like to use pip with PyProject.toml is I don't have to do all the crazy shit to like run my specific Python module. This project.scripts, I can just say, hey, from the pipelines module, just run a main function. And then in my init.py, I export that main function. So if you do this, and you do the pip install stuff, like I put in the README, I just type pipeline, and it runs. Don't have to do Python, file, module, all that shit, just pipeline. So what's happening here is Spark sets up the JVM. It also actually opens up opens up a web server, which actually shows you the running process, which is pretty cool. Sorry, I don't need all my personal stuff up there. Not that there's anything I necessarily want to hide, but I don't want distractions. So this kind of shows the progress of the different operations being executed by Spark. So in this way, I could see why people would think it's a pipelining system, but it's really not. So this is kind of cool. If we set this up as a standing server, we could browse around, look at the environment, look at what storage is available, look at the different executors, all this kind of stuff. But we're not doing that for now. Okay? And then from that example pipeline, you see it does some calculations, whatever. It's all good. Okay? And then the JVM shuts down and everything is cool. Okay? Don't worry about this stuff. It's just some random example code. But in terms of what happened, did that make sense? We ran Spark. We ran our Python program. It started the Spark session, which stood up the JVM, connected to the JVM, submitted the work that we wanted to do, this little mathy stuff down here, sent that to the Spark JVM, ran the logic, output it back to PySpark, done. Okay, so far so good? Cool. Now then, let's go back to our example.py and let's switch these back from the old pipeline to the new pipeline. And I tried to make it like a proper pipeline where like you define your different pipeline steps in various places, and then you have your kind of main pipeline flow, and then you just say, hey, read the data, process the data, clean the data, format the data, output the data, right? That kind of thing. And all the actual logic is obfuscated in the individual tasks. Because I was trying to make it like a pipeline, even though this isn't really a pipeline system. So first we read the inputs. Now, hopefully your data has finished download. Oh, right. Sorry. Important thing. Once you have downloaded the data, you want to unpack it to a folder named data in your project folder. Okay? And then you'll get like 500 megs of CSVs. So many CSVs. All of the CSVs. And it's just data. The CSVs are organized like a SQL database, damn it. That's why I don't understand why we're using frames. But maybe it's just because I chose this data set. Maybe that's why. I don't know. But unpack that zip file you downloaded of the example data to this folder, to a data folder in your project. Okay? That should only take a few seconds once you've got it set up. But I'll give you guys a minute to figure it out. All right, who does not have their data unpacked yet? Oh, everyone's got the data extracted already? Okay, awesome. All right, let's do it then. So, what we do here is we have our inputs, and then I just show some data as a sample, okay? And then I have some calculations here to get accreditation stats per university. And then we're going to dump the output into a CSV file, all right? Now this dump output, this accreditation stats, and this read inputs, these are custom functions that I made, okay? And we're going to dive into them in a second. But before that, I want to show you what exactly it does. So what this system is going to do, it takes a minute to run. It imports all the files, which we actually don't need, but I wanted to set this up as a workspace where you could play with stuff. Especially because I wasn't able to prepare as much as I wanted. I wanted to make sure that we at least had a workspace, and then maybe we could play with stuff together and kind of discover things. Yeah, it's fine. It's fine. So what it's doing now is it's going through all of those CSVs and loading all of them. Okay? Then what it's going to do is it's going to join some of those CSVs, actually not some, it's going to join all the CSVs together in some ways because they're split by year. Okay, so it takes all the CSVs for one type of data among the various years and it groups it all together. What's up?
Can we see what's the memory
Oh, that's a good idea, actually. Let me. Yeah, so finished. But yeah, I'll run this again and we'll check that. Let me just check the outputs first and then we'll come back to it. And so what it outputs is accreditation stats for various universities in India. So you see Annamalai University, shit. I don't know how to pronounce this stuff, I'm so sorry. And then you see the max score and the average score by the accreditation institutions, okay? So that's the kind of stuff we did. Now you might be like, Beege, like, this is like a 5-line SQL query. What's the big deal? Well, the big deal is a huge amount of data. So that's where this stuff becomes useful, okay? So this 500 megs is actually like a little small. In the past, when I've used Hadoop-like systems, we were working with like a petabyte of information, which is definitely not going to fit on one computer. So distributed systems like this are very useful when you have huge amounts of data. This 500 megs is not enough to really merit using Spark, but it's good for demonstration purposes. But to your point, San, let's go ahead and run this again. Let's get some HTOP going here. And let me hide this so we can see our output. And let's run the pipeline. Yeah, the VS Code server takes up so much memory, it's stupid. So let's see here. Oh, you see the JDK came up, or the JVM is up. Still not taking up as much memory as VS Code. Microsoft. But it's still taking up quite a bit. What is this here? This is... So it's taking up two of my CPUs. Two CPUs worth, well, just under two CPUs worth of load. Not much memory, actually. So what Spark's going to do is it's going to kind of like... Yeah, it's going to try to figure out like the most efficient way. One thing I should have put it in the presentation. When Spark was like starting out, they did a contest of like who could handle the most data the fastest. And when Spark was compared with Hadoop, Spark did it for the data set that was being processed, for the operations that were being executed. Spark and Hadoop, they did the same operation. Yeah, it's finished already. So it didn't get up to too much memory, actually. But the CPU went nuts. So, but that's good. That means it's being efficient. But the Spark was able to run the data challenge in 1/3 of the time with 1/10 of the compute. So like if Hadoop had like 100 servers running, Spark did it with only 10 servers in 1/3 of the time, which is nuts. That is a huge, massive, massive improvement. And that's why Spark shut up super quick once it came out. Everyone's like, oh, Hadoop was great. Spark is way better. So that's why Hadoop kind of disappeared. And then everyone started using Spark just because it's so much faster. Now, when I say faster, I don't mean real-time faster. You can use Spark for real-time. It does have a real-time streaming API. But it's not it doesn't operate on individual records. It creates just tiny batches and does it that way. Which you might argue like, isn't that kind of how real-time works anyway? It's like, yeah, kind of, but it's not as efficient as it would be if it was designed specifically for real-time. So it's more of kind of a hack on top of it to make it compatible with real-time systems. But yeah, does that make sense so far? Okay, so let's dive into actually processing some stuff. So first, let's go with reading input. So so I do some cleanup just to clean up my output directory. That's just Python stuff. You can ignore that. Yeah, that'll work. Honestly, most of the time, if you're dealing with unstructured data, it's going to be JSON or CSV, most likely, or worse, Excel files. And then you should tell them to just export to CSV. But chances are those large data that you're dealing with is going to be JSON or CSV in most cases. In an ideal case, it'll be an HDFS. But in those cases, you probably have like a whole data engineering team supporting you. So yeah, that would be a nice life. But for those of us who don't have such luxuries, CSVs. So what this function does is I do a bunch of path nonsense to basically grab our CSV files. And then here's how you read files from Spark. Now, there are two different ways to do this. I just did it this way because I didn't want to spend time figuring out the other way. But the Spark, remember, the Spark session, okay? From the Spark session, we can access the read module for reading files or SQL or whatever. And then, I tell it, hey, there are headers in the file. Use these headers to denote the column names, okay? Then I tell it, hey, it's CSV formatted data. And then I load the actual file path. And then I wanted to do this because I didn't want to lose this information. In our data set, the survey, or the data that we got, was done by surveys. And the surveys were done every year. But the year is not in the file. The year is part of the file name. But if I'm joining all the files together, and I'm not using the file anymore, I lose the file name, right? So what we do here is we have some logic here to basically pull the year out of the file name and add it as a column to our data. You can do this. You can arbitrarily add columns to the data. This is one of the key aspects of Spark. If you were to do this in SQL, you would need to select the data into a new table with a new schema and make sure to calculate that column when you do your insert. With data frame-based systems, it's just another line of code. Hey, here's a column. Here's a column name. Here's how you should derive the data. Done. That's actually really nice. That's a big improvement on the data management API. Okay? So now you might be looking at, Beege, what the hell is this F shit? You always talk about like make your variables well named and clear and all that kind of stuff. And you're absolutely right, and I hate this. But I was following convention. So in Spark, they have this kind of functions library, which has a bunch of basic commonly used functions, like your min, your max, your last, your split, all this kind of stuff. So you might be wondering, hey, Beege, if you're just getting the input file name and you're splitting and you're like getting the element at, can't you just do that in Python? Normally, yes. But I have a challenge for you. Am I doing this calculation on a single string? The input is. But the output and kind of the environment is not. This is where thinking gets a little bit funky if you're not familiar with data frames. You have to think a little bit more like SQL, and even then it's not quite right. So that input file name function there, that's a built-in from Spark. So we have to pull that from the module. So that's fine, that's normal, that's understandable. But you might be looking like Beege, there's a split function in Python. But that split function will just operate on a string. Okay? At this point, this is not a string. Okay? The input file name is not a string, which is funky. In this context, it is a column. And this is where we start to get really into kind of the data frame land, okay? I mentioned earlier, data frames are tables composed of rows and columns, okay? When you do operations, most of the time they're column-based because we're doing like data analytics, right? It's usually aggregations, divisions, all this kind of stuff. That usually happens at the column level. So when you do operations on data frames, you almost never work with a single individual value. You're usually working with a collection of rows, or more likely, with a set of columns. And maybe some rows are filtered out or whatever, okay? So what's happening here is, it's getting the input file name, and it's converting it to a column that will fit into the data frame. So it's not just a single string. Normal Python will not work here, because it's a column of data. It's a column of strings, not just a string, okay? And then we need to use their split function to operate on the column, their element at function to access an index in the list that we made, which is really funky to think about. Because what's happening here, oh, I wish I had a whiteboard. I might require, oh, I do have a whiteboard. It wouldn't work well for the recording, so I'm just going to try to be very descriptive, okay? what happens is we have basically, the file name is like, 2011, 2012 university.csv, right? That's a file name. But what it does is, it's looked at how many records are in this data frame, right? So let's say there's 1,000 records in the data frame. In reality, there's like 60,000 something or whatever. But it basically takes that file name and it makes a column where every row in the column is the file name, just 1,000 times, which is weird, okay? But maybe this can kind of help you start to visualize it. So we can't use just a normal split, because in Python, what does split work on? Strings, yes. Is this a string? No, so a split does not make sense. So, but they have their built-in APIs, they have the split function, which will operate on every single value in that column, okay? Now, in reality, in memory, I doubt they've actually cloned the column a whole bunch of times, because this is the thing with columnar storage, right? We're getting into some data theory now, but this is useful to understand. With columnar storage, the way it works is you store at least I'm pretty sure, I haven't looked at the engines in a long time, but you store the column value, in this case, the file name, and then you store a reference to every single row that value shows up in, okay? So let's say we're working with people data, and let's say we wanted to look at the sex of people, male or female, okay? You would have male, right, as one value in the column, and then female as another value in the column, and then that's it. Even if you have millions of rows. Because what happens then is that male value in the column gets mapped to all the millions of rows. The female value gets mapped to all the millions of rows. That's how columnar storage works. And that's why aggregation is so fast. Because rather than look through all the records and try to find that value in that column, you start with the column value, and then you do the mapping. That's why columnar storage is faster for analytics. Does that make sense? Does it actually make sense? Cool. Maybe. Maybe not. Should I whiteboard anyway? I don't know. Let's run with it for now. But anyway, you understand this is not a string. This is a column. So by doing the split operations, it does it on every value in the column, even though it's really only one value, but roll with it. And then you might be a little confused here. You might see this, and you're like, okay, Beege, you're accessing an index of a list. That's fine, cool. But then there's also this element at. Why are you doing the same thing in two different ways? Well, because the Spark API kind of, what's the word? I guess overrode or overridden or whatever that is. The indexing operator, basically the square brackets. But it only works for 0 and up. It doesn't work for negative values. So we have to use the element at, which does the same thing. It's basically pulling out something at some index. And then I'm using -1. So that's why. But this is a bit convoluted, but it does act as a good example of how you can't think in terms of individual values now. Now you have to think in terms of set logic. You have a column, which is a set of row references, and you have to do operations on that whole set. And that's where stuff gets funky. So that's the important part. Does that make sense? I can't tell if you're like, yeah, and I'm bored, or if you're like, it doesn't, but I don't want to speak up. It is okay to speak up, because that's why we're here, to help it make sense. All right, I'm going to go on ahead. But if something doesn't make sense, please stop me, okay? Otherwise, we're all just wasting time. And then, I do some funky stuff to get the name of... sorry, going back to our logic here, getting away from theory. What I do is I read each file into a data frame, and then I take that file, and if we look at kind of how our stuff is organized here, you'll see there's 2011, 2012 course, and then there's 2012, 2013 course, and then there's 2013, 2014 course, 2014, 2015 course, and so on and so forth like that. I don't want to have it split by year. I just want to have a course data frame, and then the year is included. Okay, that's what I'm trying to do with this data transformation here. So basically, I grab the name, and I yank out the year stuff. Okay, remember, the year is already added to the data frame data. Okay, but now I want to be able to say, hey, here's the course data, here's the university data, here's the student data, right? Regardless of the year. So I basically take the path name, I remove the CSV part, I take off the years, which are separated by underscores, and then I get the data name, and then I make a table for each type of data. So there's a university table, there's a whatever table, whatever table. Why am I calling this a table? Because the data people call them tables. In reality, they're just data frames, okay? But they are sets of rows and columns, which are tables. So often when you talk with data scientists, they might talk about tables, and they're not talking about a database table. They're talking about a data frame that they've probably written to a file somewhere, okay? So that's going to be some terminology that will be a little bit confusing. Because I remember the first time I talked to our data engineer, he's like, yeah, pull it out of this table. I'm like, you have a database? When did you get a database? What? He's like, yeah. There's this table here, and it's in Google Cloud Storage. I'm like, databases don't live in Google Cloud Storage. Google Cloud Storage stores files. Because of them, a file is a table. Okay? To them. You can tell I don't consider myself a data scientist. So that's how we pull out all the data. And then so this dictionary is the kind of name of the file, right? So in this case, university, okay? So it's the name of the type of data. In this case, university is the key, and then the value is a data frame, okay? So data frames have this method called show, and the show method is a nice way to kind of peek at the data in the data frame if you just want to make sure that you got your columns right, okay? So when we, I didn't want to make a new terminal. I wanted, my old one, great. When you see this is that university.show. So this is showing our university data. Now it doesn't format well because there's too many columns, but it basically displays the university data. By default, it shows, I think, the first 10 rows, the first 20 rows, okay? There's other stuff you can do too, but it's just a nice way to peek at your data. All right, so far so good? Cool. And then let's get into some actual data processing. So I have my tables dictionary, okay? And this dictionary consists, again, of the type of data as the key, and then the actual data frame as the value. And let me, this line's a little bit longer than I would prefer, but it's fine. So what I do is I grab so what this is doing is it's going to calculate the accreditation stats per university, okay? Apparently the way it works in India, I know nothing about India. Each accreditation authority, when they accredit a school, they include a score, okay? I don't know what that score means. I don't know what the scale is. There's just a score. I wanted to do some math. That was it, okay? So what I wanted to do here was I wanted to get the max score and the average score because maybe a university was accredited multiple years, okay? And I wanted to figure out that kind of stuff. So what we do is first we grab the data frame for accreditation, okay? Now, this data set is really organized like a relational database. So we're going to treat it like a relational database, but we're going to use the data frame API, okay? Then we join it, very much like a SQL database, to the university accreditation table, which is a linking table, if you're familiar with relational data design. And then we join it on the accreditation table's ID field to the university accreditation's accreditation ID field, just like SQL, okay? And then we specify that it's an inner join. Basically, if we have records that don't match to a corresponding record in the other table, throw it out, okay? And then from the accreditation university linking table, we join to the university table. Again, we specify the criteria for joining. We want the university ID to match the university accreditation university ID. Okay? And then once we have done that, each one of these operations, each join operation, produces a new data frame. Okay? It is not an in-place operation. It generates a new object. Okay? Now that's very nice because you can do this method chaining. You can just keep chaining methods. And when you look at example data frame code, whether it's Pandas, Polars, Spark, whatever, you'll see that they just chain methods the whole time. Okay? And then, now that we have our data joined, we can group them by the name of the university, and then we can aggregate and get the maximum score and the average score. Okay? So far so good? Then we return that new data frame as output. And then if we go back, I dump our output here, where basically it expects a dictionary, again, of names of data to data frames, and then I output it to the output folder. We make sure the output folder exists, and then we loop through, and here's the thing. You'll notice 2 pandas here. But I was talking about how pandas and PySpark are different, right? Well, you can use pandas in PySpark, because why not? PySpark, if you try to write a CSV directly, it will write the CSV in HDFS. So what it will do is it'll partition the CSV and actually create a folder and then write a whole bunch of partition files. But if I just want a simple actual CSV, the simplest way to do it is to just convert it to a pandas data frame and then use pandas to write it to the file system. Okay? Now, if you're doing actual big data, you would not want to do this because that one file is going to be huge and it's not going to be useful. You would instead want to do the Spark way and export it in HDFS, which is meant for distributed computing, distributed MapReduce stuff. Okay? But we just didn't do that here because I don't want to deal with HDFS. I don't have a good way to browse HDFS on this computer, all that kind of stuff. Okay? So does this make sense so far? Cool. And so what this does, it outputs this CSV where we have the name of the university, the maximum score it got from its accreditation authority throughout all those years, and the average score it got from accreditation authorities over all those years. Okay? I have no idea what these universities are, but yeah. Does that make sense? Cool. Questions about our tiny little pipeline here? Pipeline, quotes.
Did you run Kubernetes anywhere, or?
Not yet. We're going to do that next. All right, are we ready to get to the crazy infrastructure Kubernetes stuff? All right, this is the stuff that I find more fun, but once we finish that, if we have remaining time, we'll come back and maybe we can play with this data more and explore more of the Spark functions. Now, one thing to be clear before we do that, though, is this is the important part. This is the stuff that Spark is good at, right? Manipulating data, connecting data, transforming data, deriving data. This is what Spark does and is good at. If I had done a better job of preparing this presentation, we would be doing more than like 6 lines of code. But I'm sorry, I ran out of time. Maybe we can do a follow-up in the future if you guys are interested. But it is worth learning the data frame API. Also, one very, very important thing to note, we did not do the best thing about Spark here. There's no distribution. This is all running on one computer right now. We really should not be using Spark to do this. This is a bad example. This is a bad use case. But this is all I had the time to set up. So if you guys want, we can do a follow-up where we can actually do some distributed computing. Maybe we can just set up a Databricks cluster or something and then, do some parallel processing and all that. But I didn't have time to set that up for this time, so I apologize. But hopefully this actually gives you enough to at least get a project up and running, and then you can do that kind of stuff. Okay? So, on to the fancy, fun Kubernetes stuff. Let me collapse this. No, collapse. There we go. So, also, heads up. Shit. Okay, sorry. We should make one change because I did the Kubernetes stuff before I built this pipeline, and I did not solve the problem of having the data available to Kubernetes. So if we were to try to run it as is, it'll fail because the Kubernetes pods will try to find this data on disk, and they won't be able to find it. There are ways to do that. I just did not have time to set it up. So if you guys could do me a favor for running the Kubernetes part, and I'll update the README as well. But in the example.py, if you could just rename pipeline to new pipeline and rename old pipeline to pipeline. Okay? Because at this point, the pipeline itself is not the important part. It's more of showing you guys how to run it. Okay? So make sure to do this rename pipeline to new pipeline, old pipeline to pipeline. Okay? Good? Cool. Now, let's get into the crazy stuff. So, I'm just going to go to my README here, and I cover a bunch of the installation stuff for you. So, if you're on, oh, real quick, is anyone on Windows and does not have WSL set up? Good. If you're on Windows, you should just be using WSL. Because unless you're doing like Microsoft environment, like .NET stuff, it's just way easier to do stuff in Linux. And WSL is the best way to do Linux on Windows. So yeah. Okay. So to that end, I only have Mac instructions and Linux instructions, because if you're on Windows, you should be using Linux. So first off, we want to install Kind, which is short for Kubernetes in Docker. Basically, if you have Docker set up on your computer, what it will do is it will set up a Kubernetes cluster in Docker, which sounds funky, but it works. Okay? So go ahead and run this to install Kind if you have not already. Okay? Has everyone already installed Kind with this? No, okay, cool. We got some people typing. So I'll give you a second to run this. It should not take too long. Well, actually, Brew takes a while to update if you haven't updated it in a bit. So it could take a minute. Everyone good? Cool. And then once you've done that, you want to install kubectl. If you're not from, actually, wait, I'm sorry, real quick. Is anyone not familiar with Kubernetes? Okay. Okay. So, oh, we're okay on time though, maybe, hopefully. All right. Yeah, we'll do it that way. So Kubernetes, for those of you who are not familiar, Kubernetes is a clustering system. Okay? It is when you have a bunch of computers that you want to work together, and you don't want to manage making them work together by yourself, because that sucks. There's a bunch of problems to solve, but Kubernetes has solved it for you. So what you can do with Kubernetes is you can say, hey, here's like 100 computers. Let me install Kubernetes on all these computers, and then connect them to each other. And then I can just say, hey, Kubernetes, do this. And then Kubernetes figures out, okay, I'll take these computers and put that there. I'll take those computers and put that there. It does all that for you. Okay, you don't have to manage that shit yourself. Kubernetes is wonderful and awesome, but it takes a little bit of learning to figure out. I'm not going to teach you all of Kubernetes today. There's not enough time. But it will cover the parts that are relevant to get done what we want to get done. Okay? So, kubectl is short for Kubernetes control. Okay, it's just a little CLI utility for interacting with Kubernetes and making it do stuff. Okay, so go ahead and install kubectl, because that's how we're going to interact with Kubernetes to actually do stuff. All right, all good? Cool. I assume people were doing that while I was talking. So once we've done that, we want to actually set up Kubernetes, because Kind, Kubernetes and Docker, is just for setting up a Kubernetes cluster on your local computer. On that note, you do not use Kind in production. Do not do that. Kind is meant for you to do local development to test out Kubernetes things, okay? So Kind is just like a dev tool. That's it. Now, I copied the script, Kind with registry. What this will do is, actually before this, I need to explain something about Kubernetes. So I mentioned Kubernetes. You have a whole bunch of computers. It says, hey, these computers do this work, those computers do that work, and it just organizes all of it. How? Who has heard of Docker? Cool. So Docker gives you like an isolated, consistent environment to do some kind of task. Okay? Kubernetes is based around Docker. Okay? Once you register a server with Kubernetes, Gesundheit, and you say, hey, do some work, you provide it a Docker image, it grabs a computer, sets up a container on the computer from that image, and then runs the job. That's how Kubernetes works. Kubernetes is just running a bunch of Docker containers in a fancy way. Okay? Now, it's still absolutely necessary, because if you try to do it without Kubernetes, you're going to have a bad time. If you look up Docker Swarm, ooh boy, been there, not fun. Although I hear it's gotten better, but yeah. But if you're doing Docker, you need somewhere to store your Docker images, okay? Because Kubernetes needs to pull the Docker image to create containers from the image to do the work with, okay? So kind with registry, what this script does is, again, I just copied this from the internet. It actually does a little bit of networking stuff, but in the end, actually no, it creates, yeah, there we go, that's why I was like, this is not what I'm looking for. It actually creates a Docker registry, okay? A Docker registry, again, stores Docker images, okay? Because we don't want to mess with, AWS ECR, we don't want to mess with Docker Hub. I just want to do a local thing. I don't want to have to go create accounts on a whole bunch of stuff and make sure to pay for shit. Screw that. So we'll just set up a local registry, okay? And this is all just stuff, you don't need to know the details. Well, what this does is it sets up a Kubernetes cluster with a Docker registry deployed on the cluster, okay? So we have a place to store our Docker images and for Kubernetes to pull Docker images from to do work. All good?
What's a pod?
I didn't even say it yet, man. Okay, so a pod, I mentioned earlier that Kubernetes, when it takes one of its computers, so, all right. Yeah, screw it, why not? So earlier when I was talking about Kubernetes and I was saying, oh, it takes a whole bunch of computers and makes them work together. These computers that Kubernetes manages, we call them nodes, okay? So it manages many, many nodes. And on a node, you do some work. How do you do this work? You create a pod, okay? You can think of a pod like a workload, okay? A pod usually consists of one container. You can have multiple, but usually best practice is to have one container, except for certain cases. But generally, if you hear pod, think Docker container. For starting out, that's the easiest way to get it. So the way Kubernetes works is when you say, hey, Kubernetes, do this work, you specify a Docker image and any other configurations. Maybe it needs some sort of configurations to run the application. Maybe it needs access to some secrets like passwords or something like that. And that's all the pod configuration, which then translates to how to run a container. Does that make sense? Cool. There's also other stuff built around pods, like replica sets, daemon sets. What was the other one? What's the persistent one? What's it called? I don't remember. Anyway. Yeah, we're not going to get anywhere near that deep. No. But yeah, there's a whole bunch of stuff around pods, but for now, a pod is a workload, more or less corresponds to a Docker container, plus all the configurations needed to run that container. Good? Cool. What you can do is you can run this script, and if you have installed, kind and you've installed kubectl, you can just run the script. Actually, let me make sure is Docker running. You have to make sure Docker's running. Docker is running. You run the script. It creates the registry Docker container. It creates the kind Kubernetes cluster. And what it actually does is technically our Docker registry is running outside of the Kubernetes cluster. But our kind configurations figure out all the networking and basically make the Kubernetes cluster aware of it. So it acts like it's in the Kubernetes cluster even though it's not, but whatever. Why do we need to do it that way? Because Kubernetes needs to pull the images from somewhere, and if we don't have the registry set up, where does it pull the images from? So we set up the registry first, and then we set it up in the cluster. So now we have our Kubernetes cluster set up. If you do like a Docker PS, you will see we have the kind registry, and we have the Docker registry, which we named kind registry, and then we have the Kubernetes control plane node, which runs the whole Kubernetes cluster. Okay, because we're running Kubernetes in Docker. Now, this is not the normal way to run Kubernetes. Normally, you do not run Kubernetes in Docker. Normally, Kubernetes manages Docker, usually sits on top of Docker. It sits, or rather, if we're talking about the stack, it runs underneath Docker. It runs on the physical machine directly, and then sets up Docker containers. But we use kind for local development because I don't want to have to do all the setup of a Kubernetes cluster. I just want something fast and easy. Again, do not use kind in production. Right, and then if we want to check kind of info, we can basically just copy this command, and it shows us information about our Kubernetes cluster and all this sort of good stuff. Okay, so we have a Kubernetes cluster. Yay! All right, now we do have to do a little bit of setup. So Spark is a distributed computing system, right? Distributed means it wants to do a whole bunch of different workloads. If it's going to talk to Kubernetes to ask Kubernetes, hey, do this workload for me, right? It needs permissions to do that, right? The Kubernetes cluster needs to say, hey, I know what Spark is. When Spark tells me to run some workload, I will do that. So this sets that up. So this creates a service account in our Kubernetes cluster, and it sets up permissions for that service account to be able to basically edit the cluster by creating jobs. So we can just run these commands, and you see it creates the service account, and then it gives that service account a permissions role. Okay, not rocket science, but it's something we have to make sure we do, otherwise it will not work. And now, welcome to my own personal hell. Spark ships with Python 3.8.10. The latest version of Spark ships with a version of Python that is 3 years old. What the hell? Python 3.8 goes end of life in, I believe, October or December this year? And it's still shipping with Spark. I'm angry. I'm very angry. This is bad practice. I have opinions about data scientists. Anyway. Yeah. So, what I did was I made my own Docker file to basically take the Spark image and kind of forcibly update it to Python 3.12. Which, this looks very simple. It took way too long to figure out because, fun fact, on Ubuntu, Python 3.12 ships with setup tools version 45. If you want to actually use pip, setup tools version 45 is too old. Do you know what version we're on of setup tools currently? 70. What the hell? So it took me a bit to figure out what that problem was, why it was happening, all that kind of stuff. But I have solved that problem for you. You do not need to worry about that absolute madness. So what this Docker file does, it creates a new Spark image with Python 3.12 installed. It configures Spark to be aware of that new version of Python and to use that new version of Python by default. So you don't have to worry about that nonsense. Okay? Good? Great. Also, god damn it. But it works, so it's fine. So what you want to do is you basically want to copy these two commands. What this will do is it will build that new Docker image, and then it will push that Docker image to our local Docker registry that we made when we set up the kind cluster. Now, mine's going to be way faster than yours because I already have the Spark Docker image downloaded, and I already have past builds of the Python install. So yours is going to take longer. That is normal. That is expected. Okay, so you just wait a couple minutes, and then once it finishes, it's having a damn conniption over here. There we go. So you can see like it was already built. All the Docker image building was pulled from the cache. Yours is going to have to actually do the build, so it's going to take you some time. And then once the build finishes, it pushes it to our local Docker registry. Okay? So I'll give you a couple minutes to wait for that to run. Oh. We should have just made it easier to set up SQL databases. Then all this nonsense wouldn't have happened. Or we should have figured out a way to do like distributed columnar databases instead of all this file nonsense. Like, guys, come on, really? Now, granted, I'm not as smart as the people who figured that stuff out and actually built it. Maybe there are challenges that I'm not aware of that make it too difficult to actually work. Like doing ACID in a distributed manner is not happy, and that's why NoSQL systems have all sorts of ups and downsides because they can't be ACID while being distributed. But there are smart people; they can figure it out, right? Anyway, is everyone's stuff done building and pushing?
Just waiting the pushing.
Okay. So I'll just kind of explain the next part while we're waiting for it to push. Then I tell you to download the data. So that's all good. And now this is, because you already downloaded the data. This is the part where we actually run our stuff. So that Spark image that we're building and pushing now, or that's pushing on your computer right now, we're just using that as a base image, okay? Because I don't want to rebuild the whole thing every time. Yes, there's caching and all that kind of stuff, so it wouldn't actually rebuild the whole thing, but it just feels cleaner to have it separate. Or maybe you want multiple Spark jobs and you just want the base image that you can just build on top of. So that's why I separated it into two different images. Because I want to make this as useful for you as possible. Maybe you could reuse this and do a separate project later, who knows. But this will actually build our application with our Spark pipeline that we wrote over here, our pipeline in giant air quotes. So this other Docker image, you can see it's much simpler. First off, apparently the Spark user doesn't own the working directory. Or I'm sorry, no, that's not true. That's not true. I was confused. I actually didn't know this about Docker. When you add files to the Docker image, by default it does it as root. If you want it to be owned by some other user, you have to tell it to set the ownership as that user. The Spark image runs as the Spark user, not the root user, which for security purposes is actually good and the proper way to do it. So good on them for getting that right. And then, we add our project directory to the working directory in the Spark image. And then, we do our dependency installation. We move our, well, this is just pip stuff. Okay. This works. Okay. And then we say run our main file. Now, we have time. I'll get into it. So what happens here, by doing a pip install of the current directory, what it actually does is it installs it into the Python site packages. It installs it as if you were installing a third-party library off of PyPy, right? So we don't actually need it locally. And then I just kind of move the main.py, which triggers the whole thing, to the kind of working directory, and then I get rid of the rest of the project. I absolutely did not need to do this. We had to do a pip install anyway to make sure we installed the dependencies, and I didn't want to have two copies of the project. I wanted the image to be as tiny as possible. So rather than duplicate like 20 kilobytes of files, I deleted some files. That's all it is. Over optimization, I'm sorry. And then we say, hey, using Python 3.12, run our pipeline. Okay, so that's what it does. And then we build that image, we push that image to our repository, and now here's where the magic happens. So with Spark, there's actually a whole bunch of nice little command line utilities, but I don't like to use them. I prefer to just have code and then just run one command and be done with it. But one of these nice little command line utilities that Spark provides is Spark Submit. And what this can do a bunch of stuff. If you have a standing Spark cluster, it can send a job request to that Spark cluster, which is quite nice. Alternatively, if you have a Kubernetes cluster, what it will do is it will just send a message to Kubernetes and say, hey, Kubernetes, stand up a Spark driver node and then set up workers and like do the job. And that's cool because you don't actually need to install Spark on your Kubernetes cluster. It'll just run it when you need it, which is pretty cool. Now, if you're running Spark jobs on a regular basis constantly and you have a whole bunch of different users who are going to use Spark within your organization, this is not the way to go. It's better to set up a proper Spark cluster on your system and then have people submit to that standing cluster, and that way you can always have the web portal up, you can have people monitor their jobs, all that kind of stuff. But for our purposes, we just want our one job to run on Kubernetes. We don't need a standing Spark instance, so just go. So what this does is this basically says, hey, our master Spark node, which doesn't actually exist, will be on our Kubernetes cluster, and this kubectl command will get the address of the Kubernetes cluster to feed to Spark. So Spark will then talk to the Kubernetes API and submit the workload request. Okay. Then we tell it, hey, we're doing this with a cluster. We can give it a name. And then we have to tell it a little bit of configuration about how to run the Kubernetes jobs. So in Kubernetes, there's the idea of namespace. It's just a way of grouping stuff in Kubernetes. When you create a Kubernetes cluster, there's a namespace automatically created called default. So we're just using that. Sorry, let me check that. Sorry, it was just the ice machine. And then we have to tell it which Docker image to use. Now, we need a Docker image that has our pipeline code because that's what we want to do. So we tell it, hey, from our local registry, use this Docker image that we just pushed in these steps here. Okay? And then lastly, we tell it, hey, use this service account. Remember, we did the service account setup so that Spark has permissions to create the workloads. And then we say, hey, this is the file to run that will trigger everything. Our main file that sets up the Spark session and executes our pipeline. Does that make sense? Great. So now, copy, pasta. And so what will happen is it'll build our new Docker image. Oh, right, I'm going to have to do all this stuff because I did change my project. But yeah, anyway, we'll both have to do this, so that's good. So it's going to build our Docker image. Now it's built on top of the Spark image that we did before. What's up?
Sorry, can I ask
Yeah.
So once we downloaded the data to the data folder, in the Docker file, you mentioned that add like everything in the workload to the workbench. So
Right.
is it copying all the data which you want?
No. So right before we started this Kubernetes stuff, I mentioned that, I didn't have a way to get the data into the Kubernetes image. The data was only for when we were running the new style of pipeline locally. I didn't have a chance to get the data accessible in Kubernetes. There is a way to do it. You can tell the Kubernetes cluster, hey, here's a location on disk. You can just mount this as a persistent volume. But I didn't have time to set that up.
So like when we run the Docker file, we will not see the actual Excel files on the
Right.
container.
Right. And that's why towards the beginning I asked that you change the names of these functions, because the old pipeline is just a standalone thing doing some random math. The new pipeline depends on those files. So that's why I had you switch them. So yeah, we downloaded the new Spark image. Then we basically add our local files to the, oh no! Did I not? Oops. If you want to make this faster, add the data folder to your Docker ignore. That way it's not copying 500 megs of information to the thing. That's why you asked. Yeah, that was not my intention, so I'm actually going to kill this. Oh god. Well.
That's why I ran out of disk space.
Yeah, because you're basically duplicating the 500 megs.
I have 1 gigabyte for you.
I'm sorry.
It's out there.
Oh, apparently, even though I control... Oh, context canceled, but it's doing it anyway. Oh, it only canceled the first command. That's why. Please? So yeah, I apologize. I missed that. Please add the data directory to your Docker ignore. Otherwise, it's going to try to copy all the data into the Docker container. I'm sorry about that. My mistake.
So why is it as big as your root?
All right, but now, let's just paste this again. Now the build should be much faster. There we go. So now it's going to install our dependencies.
And in the Spark submit,
Yeah.
there is no copying or pasting data, right?
Nope.
There is nothing about it.
No, we're just telling it, hey, use this Docker image, and the Docker image has everything we need to run. Spark is big, 300 megs. Oh, we're doing perfect on time. It's great. Actually, I was hoping for a little bit more so we could mess with more actual Spark stuff, but I think people find the infrastructure stuff valuable, so it's worth it. So we're almost finished building. We finished installing our dependencies. After that, it just has to do a little bit of cleanup, and then we're good to go. Eventually. Doing okay?
What is Docker push actually doing? So we are building, and the next line Docker push. What is it actually doing?
So the Docker push, remember we set up our own Docker registry? It takes the image that we built locally and pushes it to the registry. The registry is a server responsible for managing Docker images. We need to push it to this server so that the Kubernetes cluster can pull it from that server.
So without it, Kubernetes cannot see the...
Correct. Without the Docker registry, Kubernetes has nowhere to find and pull our Docker image. Now, if... go ahead.
When we actually say Docker push, is it also like pushing the data too? Like if the data was included into the...
If the data was included in the image, it would push the data too, which is why I was like, oh shit, oh no, we need to add the data to the Docker ignore. Yeah, sorry about that.
Wait, why do we need a registry? It's like if I pull from GCP, it just gets stored locally somewhere.
Right, but is the disk in the Kubernetes Docker container the same disk that's on your host? Physically, yes. Logically, no. So when you run a Docker container, it has its own file system, completely independent of the host file system, unless you mount stuff into it. What I would have done if I had had the time was I would have actually mounted it into the container, but I didn't have time to set that up. So even though the Docker image is on your host disk, it's not in the Docker container disk, the Kubernetes Docker container disk. Because remember, Kubernetes is running in this Docker container. So the image is not there. So when you set up this registry server, when we set up the kind cluster, we let the cluster know, hey, here's a Docker image server. You can go here to pull images. And so from our local system, we push to the server, and then the Kubernetes cluster pulls from that server to deploy the workloads. Does that make sense? Cool. So now we actually have our Spark cluster running here. What happened is it submitted the request to Kubernetes to run the Spark job. And then if we do like a kubectl get pods, ooh, my system is not happy. Oh, damn it. Interesting. We can see that Spark has submitted the workloads. Now this image pullback off, what that means is it had a problem trying to pull the image. And so it was like, hey, let me wait and let me try again. So that's what's happening. But maybe that was because I accidentally ran it earlier when we had the data problem. So I think I just never actually canceled that one. But this other container is still creating. If we do kubectl describe, describe pod. Okay, so it's pulling the image. Oh, it finished pulling. Okay. So now, oh, the job is running. We can see our example application is running in the Kubernetes cluster. The way that this works, the image that we created, right? In Spark, there's the idea of a driver, okay? The driver kind of manages the job, okay? So the Spark driver is like, here's the core logic. I'm going to spin up 100 different workers to actually execute it. So the driver is kind of orchestrating the workers, okay? So that's... Uh-oh. That's not good. Oh, apparently we're reconnected. Okay, great. But the driver said, okay, I want so many workers to actually execute this job. And then the driver kind of manages all that stuff. Okay? So, it's probably been long enough now. The job is completed. And what we can do is we can do kubectl logs, and we can look at the logs here. And we can see here, this was the output of our Spark job. Now, normally you would want it to write to some kind of disk or insert to some sort of database somewhere, but in this case, we just print it out to the console. So this was our pipeline running, the old pipeline, the one that I copied off the internet, and that ran properly on our Kubernetes cluster that we triggered using Spark Submit. So does that make sense? Cool. So if you have a Kubernetes cluster up and running, you can basically package your project into some Docker file, some Docker image, push that to some registry that your cluster has access to, and then the cluster can just pull from there. Why did I show you this? Because remember, if you're running Spark on just one computer, why are you using Spark, right? Chances are you're going to need to use it when you have a very big, broad distributed system. Kubernetes is made for managing big, broad distributed systems. So usually you would either have the Spark cluster set up directly, because Spark can also run as a cluster, or if your company already has a Kubernetes cluster, which it probably does if it's doing these big distributed workloads, it would run Spark on that Kubernetes cluster and then let Kubernetes handle all the orchestration and stuff like that. Okay? So that's why I wanted to show you this Kubernetes side of things, because that's one of the main ways that you do big, giant distributed workloads. Alternatively, there are Spark as a service companies out there. For example, Databricks, who actually maintains Spark. They provide Spark as a service. And you'll see lots of people actually use that, because if your company has so much data that they're using Spark, chances are they have a lot of money. So they're perfectly fine paying for Spark to be managed as a service rather than needing to manage it themselves. But this is kind of one of the harder modes of doing it. So I just wanted to show you this way to help you get some kind of understanding. Sound good? Cool. So that is everything I had prepared. Any questions?
So what does Databricks offer besides just Spark?
It's mostly Spark. So that marketing, man. Okay. Apparently they do AI stuff too. So basically, no. Let's see, platform overview. All of the marketing bullshit. Ugh. God.
That's just buzzword.
Yeah, pretty much.
You don't need to know what we do, just buzzwords.
The AI thing.
Intelligent engine.
Here, how about we just search Databricks Spark?
Money, please.
There we go. So yeah, you can run Apache Spark, which can talk to all these data sources and do your data processing. That's another key strength of Spark that I forgot to mention earlier. I'm sorry. Whereas with SQL, you're in SQL. That's it. You have your database, and that's all you can talk to. With something like Spark, you can pull from a whole bunch of different data sources and merge all the data together and do whatever the hell you want. That is a key strength of Spark. Now, other systems can do this as well. Pollers can pull from various types of file systems. It can also pull from SQL, all that kind of stuff. But many of these kind of data frame related systems, one of their key strengths is being able to pull from a whole bunch of different kinds of data sources and treat it all as one blob of data, basically. So yeah, it looks like, here we go. This is more of what I'm looking for. Oh, maybe not. But I did see somewhere that, there's also a Delta Lake, which is quite nice. So when you have, if you're using files to store all your data, right? With a SQL database, everything must be structured, right? You must have a table that must have a name, that must have certain columns of certain data types, right? With a file, what constraints are there? You need a file name. Pretty much it. You can put anything in there, right? So what happened was, when people realized, we can just use files for storing our data, and they can be in all different kinds of formats, and the files can be anywhere on the file system, shit got to be really messy. And then you had files scattered everywhere, and then you're like, wait, we had some analytics somewhere. Crap, where is that file? Because none of us have ever had that problem before, right? Losing files is a big, giant problem. So then there was the concept of a data lake, where a data lake is basically, it's just fancy file storage, but you have certain rules about where you store files, how you name files, even how you access files, okay? And it's meant to be as a single place for managing all of your different data files. Now, a data lake is not a product, it's an idea. There are many different types of products that are data lakes. Now, another problem when you're using a file-based workflow is, now it's not so much of a problem, but in the past, if you wanted to have some file of some data, but then you needed to change it, you don't necessarily want to change the file in place, right? Because you don't have a backup, it's just a file. You have to make a backup. So instead of editing a file, what you would do is you would make a new file, and then you would version that file. But now you basically duplicated your storage, right? You doubled your storage because you had a file that was maybe like 100 gigs, and you wanted to change a whole bunch of data, but you didn't want to edit it. So now you have 200 gigs of file, right? This is bad. This is very costly. Delta Lake, which is another product that they work with, instead of duplicating the whole file, you just create a new file that stores the differences, the deltas, the changes in the file. And so in that way, you can still, across all the files, have the current latest version of things while minimizing storage. So that's Delta Lake. That's actually really cool. I've been reading about it a little bit. We're actually kind of looking into it because we're having similar problems of oh no, we're going to have so many files. But that's more, Delta Lake is more for in-place changes. If you have more of only additive changes, you're only adding new data, maybe you don't need something like this. Because systems like Polars, like Pandas, you can just union your different files. I mean, we even did it in Spark, right? We had all those different years. We just took all the different years for the same type of data and we just unioned them into a single data set. You can do the same thing with Pandas and Polars and all that. So if you're only making additive changes to your files, no problem. But if you are making in-place changes, something like Delta Lake is useful. So,
can you use this kind of thing for the version control as well? Because we can track all the changes.
So it's a little bit redundant because Git has the versioning and the changes and all that kind of stuff built into it. So you don't really need another system to manage the changes if you're already managing the changes.
Oh yeah, it can be like something like documents.
So I wouldn't do it for kind of proprietary documents like PDFs and Word files because they're not like sequential data like a CSV. But for something like a CSV, yeah, absolutely. Yeah. Does that answer your question? Cool. Any other questions? I don't know what else Databricks offers. We could look through the website, but we'd just be looking through the website together. So, but anything else? If you are interested in more data stuff, in Korea, Spark is really big. And it is really big in the West as well, but only among the very, very large companies. These days, it seems like the data engineering community is moving more towards DBT, which to me seems really weird because it fulfills a different purpose than Spark does, as I understand. DBT is for kind of like versioning your database structure. Now, the way that, so you might be thinking like, what the hell does database structure have to do with like distributed computing and all that kind of stuff, right? Well, one of the things about a data frame workflow is it's trivial to change the structure of your data. It's just another line of code, right? Whereas if you want to change the structure of your database, you have to do like a database migration to change the structure of the table. You have to migrate all the data to the new system, and then you have to update your query. It's a lot more work to handle changes. So data scientists have gotten used to being able to change their schema very quickly using this data frame system. But maybe you have a nice database, and you don't want to like do all this crazy other shit. You don't want to have to manage all these files. You don't have to handle a data lake. You don't want to have to like do all this distributed computing. Maybe you don't have enough data to merit running on a giant Spark cluster, right? And yeah, you could use polars, but now you have these file problems like the in-place editing problem that I described earlier. So it seems like some data scientists and engineers went back to SQL using something like DBT, which can track versions of the database schema. So you can say, hey, I want a new table where the format has gone from this to that, and this is the transformation. And then it just does it. As I understand, I have only read about it. I have not tried it yet. But if this sounds interesting to you, you should go to our Discord. Because, wrong window. In our Discord, excuse me while I die. In our Discord, we have, where is it? We have this workshop suggestions. So if you want to see a session on DBT or on anything else, go ahead and come in our Discord, post a new post, and if it gets a bunch of upvotes, we'll do it. Yes, this session was not the most upvoted one, but the other stuff would have taken, well, it actually probably would have taken less time, but I thought the other stuff would have taken more time. So that's why we did this one. But we'll go back to the old priority system in 2 weeks when we do our next workshop. So right now it's looking like we might do an intro to Go, or we might do a second intro to networking because we had 2 people prepare intro to networking sessions from different perspectives, which is useful. So yeah, if there's something you want to see, please post here. Or if you like one of the things that's already posted here, give it a thumbs up. And then we'll prioritize it accordingly. So with all that said, okay. With all that said, today we covered where did Spark come from. We went from files to databases and back to files, but fancy files. We talked about what Spark is, how it's a distributed computing engine, and all this kind of stuff. We talked about data sets and data frames and how they're different from SQL and some of the advantages they have and some of the other stuff that's a bit funky. And then we went through and tried running our own Spark pipeline, quotes, along with running it on Kubernetes and setting up our own Kubernetes cluster with Docker stuff and all that nice, fancy stuff. So I already asked for questions, and we are 3 minutes over time. Additional resources, I have a bunch of stuff. I just haven't put it in the presentation yet. I'll hopefully do it tonight. But thank you all very much. Whoa, let me fix this over here. Yeah, there we go. Thank you all very much for your time and attention. I hope this was helpful for you. I don't think I've explicitly mentioned this in the past, but if there's anything you feel that we could be doing better, if there's a different way we should do presentations, different presentation styles we do, anything that bothers you, anything more that you want, please give us that feedback. Tell us on Discord, or you can DM me directly. We yearn for feedback. So any improvements you want to see happen, please call it out. Also, that QR code is for our Discord. So everyone here in the room is on our Discord, I believe, or is close with someone who is. But for those of you online, you can just scan that on your phone. The link above it is the same link. And if you want to donate, unfortunately, we are only able to accept donations here in Korea because of the way the banking system works. In the future, maybe we could figure out some overseas stuff, but we are not there yet. We are a registered corporation within Korea. We are a sole proprietorship nonprofit. We are trying to become a corporate nonprofit so that we can accept corporate donations and provide tax deductions for people's donations. Right now, if you do donate, there is no tax deduction, unfortunately. We're trying to work on it. It's a lot of work and a lot of money to become that next level of nonprofit. So we are doing our best. Now, I'm not saying that it's a lot of money to get you to donate. Like, the donations would not be enough to cover, so don't even worry about it. But it's just more to kind of offset the cost of dinner, which we're going to go have after this. So thank you, everyone, for coming. Hope you had a good time. Those of you online, please give feedback in the comments. We're slow about checking them, but we do check them. So thanks again, and bye-bye.